Okie doke. So, picking up where we left off on Wednesday, we were talking about how to decarbonize steel manufacturing. So, cement is a really good example of one of these hard to abate industries. And the deal with cement, obviously, is that not only do you not only do you produce, lost my train of thought there, CO2 from the chemical process that goes on in the lime kiln, but you also produce CO2 from the energy that goes into the furnace. And a similar thing happens with steel. In typical steel manufacturing, again, you take the iron ore, so that's iron oxide, and you have to reduce it in a blast furnace. So the blast furnace requires energy input, and during the course of the reduction of the iron ore, you generate CO2 from the chemical reaction. And then the oxygen converter that takes the pig iron and turns it into steel also requires fuel. So there's, again, similar thing where you've got both a fuel choice where you can decarbonize that, and then you can change the process of reducing the iron oxide in a way that doesn't produce CO2. And so there's several companies that have been working on this. This is one such one. It's called the hybrid process. But basically, the blast furnace does not use natural gas to power it. It uses hydrogen. So that's one thing. And the other thing that happens is that they're using hydrogen in this furnace. It's not called a blast furnace, it's called a shaft furnace, so it's a little bit different. And that reacts with the iron oxide. So rather than producing pig iron, you're producing something called sponge iron, which is a little bit different. But the basic idea is the same. And then you put it through an electric furnace that is presumably powered by renewable energy. So you can, hypothetically, completely decarbonize the process. And so, yeah, you're using hydrogen and syngas in the shaft furnace rather than using coke in a blast furnace. So again, it's possible to do this, and I know that there are companies looking at this. So it's definitely something that hopefully we'll see more of in the future, because just like cement manufacturing is like 5 to 7% of global CO2. Steel manufacturing is 7 to 9%. So if you decarbonize those, then you can put a significant dent in global anthropogenic CO2 emissions. Okay, now another thing that you can possibly do with hydrogen is use it as a transportation fuel. Now, there are some challenges associated with this in terms of cost, and also in terms of fueling infrastructure. So there are only a handful of hydrogen vehicle fueling stations in the United States right now. Most of them are in California. The only one that is not in California, do any of y'all know where it is? It is here at UT, up at the Pickle Research Campus. There's a project called H2 at Scale. It's funded by the Department of Energy, where as part of that, they have built a hydrogen vehicle fueling station. They also have steam methane reformer up there. So anyway, so they're making hydrogen and using it for research purposes as a transportation fuel. Okay, so you can fuel pretty much anything with a hydrogen fuel cell, from cars to airplanes, and there are various companies looking at doing that. I'll talk a little bit about the cost associated with this. Right now, hydrogen fuel cell vehicles are not cost competitive with electric vehicles. So this is, let's see, this plot on the left here is looking at cars, and this plot on the right is looking at trucks. And so what we've got is, so these 4 columns here, this is today, or when I say today, this is 5 years ago. Should look to see if there's an update on this. But basically, the different types of vehicles we're looking at here, this is a fuel cell electric vehicle, so that's hydrogen. And then we have two different battery electric vehicles with different ranges. Okay, so 400 kilometers and 250 kilometers. Just for reference, a typical electric vehicle like a Tesla Model 3 has a range of right around 180 to 200 miles. So that's closer to the 400 kilometer end of things here. And then this is a internal combustion engine hybrid. So this would be something like a Toyota Prius. Okay, so it's looking at the total cost of car ownership, and this is in dollars per kilometer, US dollars per kilometer. And you can see that obviously the fuel cell electric vehicle is the most expensive. And the reason for that is low utilization of infrastructure. Basically, if you don't live in California, you cannot drive a fuel cell electric vehicle in the United States right now. So that's a bit of a limitation. But theoretically, it could be possible to build out fueling infrastructure and that sort of thing. And actually, as of 2019, the IEA was predicting that fuel cell electric vehicles could compete with battery electric vehicles if the fueling infrastructure were to be built out sufficiently. It's kind of interesting also, if you look at the other portions of the cost, the other big one for both hydrogen fuel cell and battery electric vehicles is the cost of the battery and or fuel cell. And they're projecting significant reductions in those in the long term. So, that's also, a bit of a projection, but we'll see if that comes to fruition. Okay, for long haul trucks, this is also an area that hydrogen has been, touted as a potential solution for. Right now, it's actually really interesting. Battery electric long haul trucks are significantly cheaper than diesel internal combustion engines when you're running that diesel on sustainable diesel. So this would be diesel made with synthetic fuel. Okay, so synthetic diesel is pretty expensive. And so electric vehicles would be cheaper today. It's too bad they don't have kind of a normal diesel truck on here for comparison. But anyway, same point. Hydrogen fuel cell powered trucks are much more expensive to operate right now than battery electric. In the future, they're projecting that that will not really change. And so the cost with the hydrogen fuel cell powered trucks is projected to come down, but it's still projected to be a lot higher than it's going to be for cars and light, kind of light vehicles. The reason for that is if you're operating a long haul truck, you are going to be covering a lot more distance and going to a lot more places than you typically would with a car. Okay, so just as an example, I basically drive my car in Austin and I occasionally go to Houston, and that's it. Okay, so if I want to run my car off of hydrogen, I keep saying charging. I need fueling infrastructure here in Austin and then up and down 290 all the way down to Houston, right? But if I'm operating a long haul truck, I need fueling infrastructure everywhere across the country that I go. And that's a much bigger lift than it is to just do things locally. So that's the big problem with those. And, it's kind of for better or for worse, the market and or government incentives in the United States right now have prioritized electric vehicle charging infrastructure over hydrogen fueling infrastructure. So, it is what it is, but that's kind of the state we're at right now. Now, I also want to point out shipping, because that is another big contributor to CO2 emissions. It's right now, 5% of global oil demand goes to container ships, and they produce 2.5% of global CO2 emissions. So here's another big opportunity for decarbonization. And this is a plot of same thing, total cost of ownership for ships based on fuel type. So right now, synthetic fuels are going to be very expensive. These are the typical fuels that they use. It's a very low sulfur fuel oil and potentially liquefied natural gas as well. I think LNG ships power themselves off of the stuff that they're transporting. I think they burn the natural gas. So anyway, so right now, so this is internal combustion hydrogen. So this is straight up burning the hydrogen to power the ship. It's more expensive, and that's due to the cost, mainly to the cost of the hydrogen. So if you bring that cost down, you could be competitive with conventional shipping fuels. Ammonia is a little bit cheaper, but again, the cost of the hydrogen / ammonia is the main driver there. So in the long term, the IEA is a little less bullish on the use of hydrogen or ammonia as a shipping fuel. But we'll see. A lot of it has to do with how much you can reduce the red part of that column. So if we're successful and we bring the cost of hydrogen down to $1 per kilogram, which is the Department of Energy's target, maybe that red dot or that red column will come down a little bit more. So we'll see where this goes. Okay, last little bit I want to hit on is hydrogen actually a greenhouse gas? And the answer is, you know what, it kind of is, but it's an indirect effect. Okay, so there are these things in the atmosphere called hydroxyl radicals. They are negatively charged OH groups that break apart from a water molecule, and they're floating around up there, and they are what's responsible for oxidizing methane and other things that are in the atmosphere. Now, our next unit is going to be on methane emissions. And so we'll see that methane is a much, much worse greenhouse gas than CO2. But the deal is it has a much shorter residence time in the atmosphere because it does react with things and oxidize, okay? So, but we count on having those hydroxyl radicals up there to do the oxidizing for us. And the problem is that hydrogen will react with those radicals and form water vapor. And that removes the hydroxyl radicals from the air, and they're not there to oxidize the methane. And so you are increasing the residence time of methane in the atmosphere and also producing water vapor. Both methane and water vapor are very strong greenhouse gases. And so there's not been a ton of work on this, but one of the more recent papers looking at this is that hydrogen itself in the atmosphere, if you look at it over 100 years, it has a global warming potential of 11 plus or minus 5, and that is multiples of heat trapping relative to CO2. And that is because it consumes these radicals and lengthens the residence time of methane in the atmosphere. And so there's a big push right now to try to understand, if we do develop a big hydrogen economy, how do we prevent leakage from transportation and storage infrastructure? How do we monitor leakage? And what are acceptable leakage rates that we should set as part of policies and incentives? So this is something I think definitely watch out for this, because it's, I think, a bit of a, what's the word I'm looking for? Underappreciated issue with hydrogen. Okay, that's it for our unit on hydrogen. I hope you've enjoyed it as much as I have. I'm a big fan of hydrogen, so we'll see where this goes. All right, now I promised you that we were going to move on to methane leaks. So, but yeah, let's go ahead and do that. So just a heads up, Monday, I'm going to assign our final homework assignment. It'll be due the week after Thanksgiving. It's a little bit of a writing assignment. And I'm going to give on Monday a brief talk on persuasive writing. And so basically in the assignment, you guys are going to do 2 short writing samples, basically for 2 different audiences about the construction of a hydrogen pipeline. And I'll give you some more details on how that's going to work. But I'm not going to do that right now. I'll do that Monday. But for now, we're going to start this short unit on methane and natural gas supply chain. Let's see. The National Academies have a good publication. It's from 2018, but it's still pretty relevant today if you want more information on this. And I have to give a shout out to Dr. Ravi Kumar, who helped me out with some of the material for this. He's like our methane emissions guru here. Okay, so methane, obviously a great source of energy. We use it to generate electricity here on campus. That's the power plant right across the street there. However, 26 times the radiative forcing per molecule relative to CO2. So it's a very, very strong greenhouse gas. And it does only last about 9 to 10 years in the atmosphere, as long as the hydrogen isn't eating up the hydroxyl radicals, right? But once it oxidizes, it turns into CO2, which is also, long-term not a good thing. So this is just a plot of radiative forcing from different gases based on how much is in the atmosphere. So you can see CO2 is the red line. It's kind of the big dog in the house here. This is going back to the 1990s. But methane is the second. And so, it's kind of a mistake not to focus on some of these other gases that do trap heat, because if we really want to limit the amount that the Earth's surface is heating up, we have to think about the whole picture, not just carbon dioxide. Okay. Yeah. Okay, so I showed you guys a long time ago, back in August, I think, plots of atmospheric CO2 concentration. So CO2 is much more abundant in the atmosphere. We're at about 420 parts per million right now. Methane has a lower concentration right now in the atmosphere. So this is in parts per billion. So 1,000 parts per billion is 1 part per million. So we've got about 100th the concentration, but again, remember how much warming potential there is. Again, if we look at ice core data, going back to, actually this kind of bothers me. There's no year of 0, but anyway, going back over the last 2 millennia, you can see it's been fairly constant until Industrial Revolution, and then, similar thing to what we see with CO2. And the thing that's most concerning about methane emissions is that they have really accelerated. Back in the early to mid 2000s, what am I trying to say? The atmospheric concentration kind of plateaued. And then, late 2000s, when all of a sudden we figured out how to do fracking at a very large scale and produce a lot of oil and associated natural gas, the concentrations start increasing, and they're still accelerating. See, these data go back to 2022, but even over the last 2 years, the steepness of this curve has gotten more dramatic. Okay, and just to kind of hit this home, yes, there's a very strong temporal association between this acceleration in methane concentration in the atmosphere and tight oil and shale gas concentration in the United States. Question here.
with the infrastructure being built like that, the solar front as well, for natural gas, I think some of that will offset that effect, get more flaring as well. Or would that flaring be counted?
Yeah, so that's a really good question. There's this whole issue of flaring that is built up in it. So I think I'll talk about flaring later, but let me talk about it now. Okay, so flaring, for those of you who don't know, when you are drilling an oil well or a gas well, or you're producing oil or gas, if you have natural gas that you cannot move through a pipeline for whatever reason, either there's no pipeline or the issue we have right now, particularly in the Permian Basin, is that natural gas is so cheap that it doesn't even make sense to try to bother to sell it because you won't make any money with it. In those situations, you will flare the natural gas. So in a perfect world, the flare actually completely would combust the natural gas. And so you would produce nothing but water vapor and CO2, which, obviously we don't want to be producing CO2, but CO2 is more benign than methane. But most flares do not completely combust, even when they're burning. And B, they sometimes will get blown out by the wind, and then you'll just be venting methane into the air. And that's, that is a bad thing. And so, like I said, this has been a particular problem specifically with oil development in the Permian Basin. There's a couple of reasons behind that. One is it mainly has to do with economics. Okay, so natural gas is very cheap right now. Oil is relatively quite a bit more expensive. And so, the companies that are operating out there, they're not going after natural gas. They are going after the liquids. And so they produce what's called associated gas, which just, happens to come out of the ground along with the oil, which is the stuff they're after. And, they will usually just flare that stuff because it doesn't make any sense to try to sell it. The reason that the natural gas is so cheap, particularly in the Permian, has to do with lack of pipeline capacity, basically. Now, that's been relieved a little bit in the past 5 or so years. They've built some more natural gas pipelines. And also, liquefied natural gas exports have really increased from the U.S. recently. And there's, a couple of terminals on the Texas coast now that can be, offtake points for Permian natural gas. And so actually the flaring issue in West Texas has improved just over the past year or two as a result of that. But yes, going back into the 2010s, at the height of, cheap natural gas and not having any offtake capacity, that's when, they were just flaring like crazy. Even as, recently as 2 years ago, I went to a meeting in San Diego and I flew home at night, and going over the Permian Basin, it was just like, it was lit up like a Christmas tree. It was crazy how many flares there were. It's really, really shocked. So that was in the winter of 2022. Is that right? Yeah, that was. And so, it's recently it's really improved. They're flaring a lot, which isn't to say they aren't still flaring. There are legit reasons that you need to flare, to prevent, pressure buildup or something like that. But, if you can move that gas somewhere else and not just be burning it or venting it, that'd be a good thing. Yeah.
Is that also happening in North Dakota? Because I've seen like pictures at night of the United States, and it looks like this huge mega city in western North Dakota.
Yeah.
But it's all just oil flaring.
Right. Yeah. So the Williston Basin, which is where the Bakken Shale is, yes, I think that's also improved. But for a long time, they didn't. Same thing. They didn't have pipeline capacity, so there was nowhere to send that gas. In fact, they didn't even have enough pipelines for the oil, so they were just trucking stuff out of there. And it took a couple of years for the infrastructure to get built up. Because here's the thing with so pipelines are part of what we call the midstream industry. So upstream is exploration, production. Downstream is refining and chemical plants. And midstream is everything between when the oil comes out of the well and when it gets to the refinery. Midstream companies are very profit sensitive, and they will not build a new pipeline unless they can get long-term contracts for suppliers to be moving product through the pipeline. And when I say long-term, I'm talking 15 to 20 years. So if all of a sudden you have a drilling boom in some area where there hasn't been a lot of oil and gas production before, for example, the Williston Basin. It was kind of a minor basin, but the Bakken deal was so much larger than what they had going on there. You know, the pipeline companies, they're not going to say, oh, hey, we're going to go ahead and build you guys a pipeline right now. No, they're going to wait and see if this is going to be a real thing or not, or if it's just going to peter out after a couple of years. And so you end up with things like what happened in North Dakota, which is they had several years where they had, you know, a ton of flaring and really constrained ability of the producers to get their products to market. So, yeah. Where was it? Talking about methane. Okay. All right. So this is the global methane budget. Looking over the time period 2008 to 2017. So this is, again, this kind of time period of, you know, rapid acceleration of methane emissions. So we can estimate methane in the atmosphere with a couple of different ways. One is called the bottom-up approach, which is you identify all the sources and sinks, and then you try to add those up and see what the balance is. There's also what's called the top-down approach, which is kind of a modeling based. And so this uses like atmospheric circulation, satellite observations, and that sort of thing. I'll break it down a little bit on the next slide. But there's, you know, based on these two methods, they generally agree pretty well. So for fossil fuel production and use, you know, they estimate, you know, somewhere on the order of 100 to 120. What are the units on here? I think it is, oh, come on, guys, y'all don't have the units? Oh, yes, teragrams of methane per year, okay? And so that's what's coming out. The other big source of methane, which I think we're all aware of, is agriculture and specifically livestock. That's a big, you know, cows are a big source of methane as well. In fact, it's almost double what we have from the oil and gas industry. So those are our big sources of methane. There's also some that come out of wetlands as a result of natural, anaerobic digestion of organic material. So those are the main sources. Okay, so total emissions are somewhere between 500 and 700 teragrams per year. Now the sinks over here, basically there's the chemical reactions in the atmosphere that we've talked about. That's the major sink. And then there's a little bit of uptake in soils, but dominantly you're looking at oxidation in the atmosphere. And obviously the sources right now are larger than the sinks, which is why we have increasing atmospheric concentrations. But that's generally what the methane budget looks like. Now, yeah, a little bit of a side note here on the bottom up versus top down estimates. So, the bottom up is you do all of your observations and you add them all together for all the sources and sinks. And top-down models, use these inverse models that involve global atmospheric circulation and observations and that sort of thing. Okay, so yeah, that's how you get your bottom-up budget, and then your top-down budget adds everything together into a model. So just slightly different ways of going about it. Okay, now if we look at oil and gas sector emissions, and so I'm just going to make a little side note here. Yes, agriculture is a larger emitter of methane right now. However, the title of this course is not Sustainability Issues in Agriculture. It is Sustainability Issues in Energy. So I'm going to pick on the energy sector because that's what I do. All right, so here's the oil and gas sector. So what you can see is, so I talked about incomplete flaring a little bit. So this is where you're trying to flare and somehow the flare goes out. Actually, the industry has done a very good job over the past 5 or 6 years of improving the quality of their flaring equipment. And to my knowledge, right now, methane emissions due to unlit flares or that sort of thing are basically minuscule. Okay, so that's actually a good thing. So that like I said, that's a good thing. The things that we have to worry about are these fugitive emissions and then simply venting methane to the atmosphere. And so the big driver of this is onshore conventional oil. And there's a number of different reasons for that. One is what I talked about a little while ago, which is that if you're an oil producer, you're not interested in the gas, and you might not even have a way of getting your gas to market. So you will either flare it, or you'll just say, hey, just open the valve and let's vent it. It's a little bit. There's also fugitive emissions, which are due to leaky equipment and that sort of thing, tanks, compressors, that sort of thing. So that's the big driver. Obviously, if you're producing gas, you're going to be emitting a lot of methane too, just due to leaks. And if you have to shut in the well or stop production for some reason, you might need to flare or vent it. But that's the big driver. The other big driver is fugitive emissions from downstream gas. Now, they don't list midstream on here, but I would lump midstream in with this one as well. And this would be, again, pipelines, compressor stations, that sort of thing. Those fugitive emissions are, a big problem. But that's what we're looking at right now. Oh yeah, the other thing I forgot to mention about onshore conventional oil. Some of those wells are very old and leaky. And so it's possible to have, fugitive emissions coming out of the well, not because you have a leaky valve or that sort of thing, but because they're actually coming up around the annulus around the completed well. So anyway, that's the big deal with that. Okay. Now, if we look at parts of the world where that have a lot of methane emissions, we can break that down by the sector as well. So as of 2017, this is a figure from the IPCC, I think, at the UN. China was estimated to have the largest methane emissions in the world, and a lot of this was due to coal mining. Coal mines are very leaky. Coal often contains methane. And it's a big deal, actually, to operate a coal mine and try to mitigate the methane emissions coming out of it. There's also, particularly in East and Southeast Asia, rice cultivation is a significant source of methane just because of the way the rice farming process works. If we look at, let's see, North America here, oil and gas is the biggest driver of methane emissions, followed by enteric fermentation. That's what goes on in a cow's stomach. So agriculture and oil and gas. So it varies. There's opportunities to cut this down. Okay, I think that's a good place to stop right now. We'll come back to this on Monday. I hope you all have a fantastic weekend.